Alright, so we're on lesson 62, page 442 in your book, actually starting on page 440. And some things that we want to review today. This may be review, it may not be, it really doesn't matter. What matters is that when we're done here, all this makes complete and absolute sense to you, and you have a very good working knowledge of the definitions, and you can use them interchangeably with one another to be able to figure out different scenarios that are presented to you. First off, as a review, you need to recognize the fact that what I'm drawing on the board here, on this whiteboard, this would be an acute angle because it is less than 90 degrees. Okay, this is an acute angle. Everybody should be okay with that. For review again, now what I'm drawing here, and it's evident by that box, is I'm drawing a right angle. Okay, that's a right angle. We've got 90 degrees here, and that is a definition of a right angle. Then we can also have this type of angle, where the angle, once we measure it, is going to be greater than 90, and when it's greater than 90, it's called obtuse. When it's greater than 90. So maybe it's 120. Okay? Acute here, this might be 70. Alright, so we review, that's a bit of a review. Also, what I want you to know is the different kinds of triangles we can have. We can have an acute triangle. An acute triangle is a triangle that has all three sides that are less than 90 degrees. There's no obtuse angles in this triangle. So this here would be an example of an acute triangle, because this is less than 90, this is less than 90, and this is less than 90. When we're naming the triangle acute, right, or obtuse, we are not interested in the length of the lines. These don't mean anything. The length of these lines do not mean anything when we're naming them acute, obtuse, or right. They mean nothing. What matters are the angles, the measurement of the angles. That's what matters. That's what determines if it's going to be acute or obtuse. So we know this is acute because all the angles are less than 90 degrees. I will draw obviously a right triangle, and we know it's a right triangle because we have our one angle, which is 90 degrees, and when we have that, we know it's right. We should also know, by the way, that the total measure of all the angles, of all three angles here, should be 180 degrees. Okay, should be 180 degrees in these triangles. So if this is 90, we don't really know what these angles are going to be. We can say it should be 45 and 45, right? We just say that they should be 45 and 45. Do they have to be? With the right triangle, you can't. They have to be 45. They have to be 45 and 45. But we're not concerned about that, actually. What we want to know is we want to recognize that this is a right triangle. And then lastly, we have an example of an obtuse triangle. Now that's an obtuse angle, right? But we want to have an obtuse triangle. We have to have three sides. And what makes this an obtuse triangle is the fact that even though we see here that it has two what kind of angles are these here? Josh? They're acute, right? So we would say, well, it's got two, if it's got two acute angles, and then we have this one angle here, and what kind of measure is that angle? This is obtuse, right? So it just takes one obtuse angle, just one obtuse angle, and that becomes an obtuse triangle. Okay, it doesn't have to have the majority, it just needs to have one obtuse angle, and that is referred to then as an obtuse triangle. Why is this showing up? Okay. Are we okay with that? So far, so good. Okay. Let me scroll down here. So, scenario. Let me get a. I don't know why this thing keeps on popping up. It really annoys me. Whatever happened that I can't? I used to never do that. This side over here, it's like this thing is getting in the way. I. It is a tiny key. Well, no, but I don't need that. I wish there was a way of getting rid of it completely. See, it's just kind of over there hanging out. There probably is. All right, guys. Okay, hang on. Not right now. Hang on. All right, so look at we have this. Oh, we have nothing right now. All right, so we're going to have a right triangle here. Okay, and this is going to be A, this is going to be B, and this is going to be C. So your book tells us when we're describing the triangles, we refer to the sides and angles of opposite each other. For example, we can say that the side opposite the right angle is the longest side of a right triangle. This is so what we have here, this is the angle, okay? And this angle, this is the side opposite the angle. And the way you can see that is, there's two ways. You can see that the angle is opening up to that side, obviously, right? Or another way you can look at it is the line is made up of the two segments that do not make up the angle. You can see that line BC and line AB or AC makes this angle, right? This line is involved in the angle. This line is involved in the making of the angle. This line is not involved in the making of the angle, is it? So then that's the angle that's going to be, that's the line that's going to be opposite the angle. Here's our angle, and our angle is looking at the line. And then for angle A, we can say angle A is opening up to or looking at line BC. Right, you see that? And then we can say that angle B is opening up or looking at line AC. Make sense? Does that make sense to everybody? Everybody with me, right? Okay. All right, so this is going to lead us to our first example. We're going to have a triangle. And this triangle is going to be W, X, and Y, and it's going to have an angle measurement of 60 over here, an angle measurement of 61 over here. And what did we say our total measurement has to be for a triangle? 180. All right, so then what is the missing angle here, Brandon? 59 is the missing angle here. So we figured that out. It should total 180, and it does. Now, the question that we have, that we're faced with, is it wants us to name the sides of this triangle in order from shortest to longest. So I'm going to put shortest, I'm going to put next shortest, and I'm going to put longest. So the way I do this, to find my shortest line, it's asking for the shortest side, I take my smallest angle. And my smallest angle is going to be looking at my smallest side. It's going to be exposed to or opening up to the smallest side, which happens to be XY. Okay? And then the next smallest angle is going to be opened up or exposing the next smallest side, which would be WY. And then lastly, my largest angle is going to be opening up or exposing to the longest line, which would be YX. Everybody see that? Does that make sense? This is a little hard to see. Okay? So we're good with that. Any questions about that? All right. You're doing good. The girls are struggling with this, but this not so much. Okay, then we have another example problem. It's given us this triangle. And it is Q, R, and S. And we know that this angle is 58. We know this angle is 61. And what it says to us is this. Which sides of this triangle are the same length? Well, how would we figure that out? What's going through our head? Isaac, what's going through my head? Okay, Cam, what do I do here? Cam, what am I doing? Jake? The total of the triangle is 180. Yep. How do I do that, Jake? $68. Dave, you want to help him? 180 minus what? I'm going to add 61 and 58 together. And that's going to give me 119. I'm going to take that 119 and subtract it from 180, and I'm going to get 61. And that's the number that goes up here. So the question is, name the sides of this triangle, or I'm sorry, which side of the triangles are the same length? And the sides that are the same length are going to be what? Yeah, SQ and SR. SQ and SR are the sides of the angles that have the sides rather that are the same length. Okay, because remember, this is opening up to SR and this is opening up to SQ. Okay, that's how we know. Those are the sides that are the same length. May not look like they're the same length. You can't go by the way it looks. My triangle is horrible, but you can't go by the way, because this is not to scale. Okay, otherwise you'd say, well, wait a minute, these sides look more equal than this side. But okay, it's where the angle is opening up to. The angle is 61 is opening up to SR, and this angle 61 is opening up to SQ. Okay, or do we see that? Okay. Yeah, if you add the angles that you know, the 58 and the 61, and subtract that from the total angle in all three, it's going to give you the missing angle, right? You can always review this, replay it, rewind it, watch it on the blog tonight, and you should be okay. All right, now, example 3 says we have this situation. J, K, and L. What it says here, JK is the same as KL, which is equal to LJ. So what is that telling us in essence, guys? The sides. Yeah, it's telling us all three sides are the same length, right? So if all three sides are the same length, what is each angle going to be? 60 degrees, right? Y'all see? Yeah, Nick? Yeah. All three are going to be 60 degrees. You see that? Now, so which side's going to be the longest? They're all equal, aren't they? And the way we can show that, by the way, guys, the way we can show that all the sides are equal, you just see these tick marks. And that'll let you know that all sides are equal. And then in here, it'll let you know that all angles are equal. So you can look for tick marks. This is an example of an equilateral triangle. Equilateral triangle. Okay, that's an equilateral triangle. Make sense? Okay. Let's see. Let's talk about an isosceles triangle. Does anybody know what an isosceles triangle is already? You already know. Yeah, exactly. An isosceles triangle is where you have at least two, not only two, at least two sides are equal in length, right? So can an isosceles triangle have three sides equal in length? Yes. That's right. Equilateral is also isosceles, right? It just has to have at least two sides have to match. If the third side matches, that's a bonus. Good for us. But at least two sides have to match for it to be isosceles. So let me clear all. If that's isosceles, then what do you suppose it would be if we had three sides that don't match? Scalene. It's a scalene triangle. Yeah, Nathan's like, my hand was up. It's a scalene triangle. Exactly right. It's a scalene triangle if three sides are different. You have three different lengths. You have three different angles. Okay, three different lengths, three different angles. It's scalene. So here's a question for you. If the perimeter of an equilateral triangle is 2 feet, we have an equilateral triangle. Equilateral meaning what? All sides are equal. So if we have an equilateral triangle whose the perimeter is 2 feet, what is each side going to be? 3/4 of what? 3/4 of an inch? 2 feet is 24 inches. Divide that by 3 is 8 inches apiece, right? Or you can, now 8 inches is 3/4 of a foot, right? So David was right. You can say 3/4 if you wanted to. I don't think it asked for it in inches, did it? Let me see. Oh, it says how many inches long is each side. It does say inches, so you have to reduce it to inches. And then next, guys, and almost lastly, it's going to ask me to draw an isosceles right triangle. What does isosceles mean? Two sides are the same. So in this case, this is going to be 5 centimeters. This is going to be 5 centimeters. And our 90-degree angle is right here. This is the right triangle. That's how we would draw it, obviously, right? Draw two sides the same length, and then we draw a connecting line, and that'll be whatever. That's Pythagorean's theorem. A squared plus b squared equals c squared. This is line A, this is line B, this is line C. You square A squared plus b squared will give you the number for c squared, but you don't have to worry about that. But do we have any questions about any of this stuff at all? Okay, we're going to do the practice set. So now, I'm going to shut this down actually, and we'll just do the practice set without this.